Let's do some examples. Sure, why not? All right, so we did that. So let's say we this marker is horrible. So we have a coin, we flip it 100 times, we get 67 tails. What's the probability of a tail? How do you know? Why?
Well, the coin has only two sides, and assuming it doesn't land in the middle. It's a law of large numbers equate to the average.
Yeah, but I'm asking you specifically on this problem. You have a coin. You get a coin. You go to Vegas, you get a coin, and you start flipping it. You flip it 100 times, you get this, 67 tails. Well, then probability of tails is 67%. We're going to get to lower large numbers in a second. But it's 67%. Why? Because the probability that we are talking about here is which one? There's observed, there's classical, and there's subjective. That's not subjective, right? It's not classical, because classical would say, hey, the coin has two sides, both are the same balance, right? The chances of having heads and tails is 1 to 1 or 50-50, right? This is observed. We are observing 67 flips, right? If I give you a die and I tell you the die is weighted, but I don't tell you which side is weighted, what do? You assume that the die is going to roll sixes with 1 out of 6 chance. We're going to start rolling it around, trying to figure out, right? Trying to approach the law of large numbers, which we will uncover very soon, right? So this is observed probability. So this is observed. Okay. So let's try another one.
Can we turn that around and make it into a classical? I mean, in order to say it's a classical probability, do we have to say it's 50-50?
We have an ideal coin and we're going to flip an ideal coin. Coin, what's the probability of getting tails? You don't have that, right? This is saying, hey, we are doing something and we're going to base the probability on what we did. For example,
So we've already done it. So it's
yeah,
internal
well,
data.
flip a coin 100 times and get 67 tails, right? Do a survey, get this. It's classical probability says we have the same, every simple event has the same chance of happening. Here we don't know if every single simple event or heads and tails have the same chance of happening. There's nothing said about it, right? If you say, hey, I'm going to flip a coin or a perfect coin, I'm just going to flip a coin and there's nothing else to it, you have to make some assumptions. Here, you don't have to make assumptions. I told you what the coin is doing, right? Now, this could be a perfect coin, perfect heads and tails, but it's not necessary, right? So, just like if I give you a coin, one coin, and I tell you to flip it, you flip the coin and it ends up on heads. Do you know if the coin has a heads on tails or has two heads? You don't know. You flipped it once, you saw the head, it landed on heads, and you're like, okay, well, it's heads. Do you know what the other side is, right? This is the question. If you are talking about classical, you need to know that both sides are different and both have the same chance of happening. All right, let's try another one. We do a poll, and the poll says, hey, we have 87 people saw the eclipse. 211 people. So let's strike a little bit closer home. So we have a poll, and we have 87 people saw the clips, 211 people did not see the clips, and 12 people didn't care to answer the question. And I'm asking you, what's the probability that a random what's the probability that a random person saw the eclipse? Again, this is not classical, right? It's not subject, this is observed. So what do we have? Well, we have 87 people saw, out of how many?
310.
Which comes out to be about
28%.
28? Should be 28 point something. 28 point? 06, so 0.1, right? We round to one more decimal place than the one that was given. So 28.1%. And again, what kind of probability is this? This is observed probability. All right. One more. What is the probability that, I don't know,
Our answer for that question, the second one,
yeah?
28.1%. On our answers, does it have to be 28.1, or can we say 1 out of 4 people saw the eclipse?
No, because 1 out of 4 implies 1 out of 25%. 25 and 28 there's a difference. Right? If you want to say about 28%, right, that's acceptable. 1 out of 4 is not. There's just too much loose space. Because in that case, 1 out of 4 would imply anywhere between 22 and 28%. That's a large gap where we want to be very specific. Right? The estimate is 1 out of 4. Right? You guesstimate. All right. So what's the probability that birds are going to poop on my car? The answer to that is about that. What kind of probability is that? That's subjective, right? It's not like I measured how many trees there are, how many birds there are, how much food there is, what the weather is, the wind, where I place the car. There's no classical approach to this, right? On the other hand, I could be one of those OCD teachers that sits there and measures every time there's poop flying in the air, like landed and didn't land, landed and didn't land. And after 20 years of parking on campus, I come out with this number based on observed. But most likely, this is a subjective probability. And here's the tricky part. A lot of the times when you look at news and reports, you will see somebody throw some percentages in. If there's no data to back it up or no appendix with raw numbers, I usually get very concerned. Because where did it come from? Right? it's, if I say, hey, there's almost 73% of my car getting pooped, the campus is going to do something about it because then probably the next car is having the same percentage, this next car, right? So that there's a decision being made, money being spent based on this. And if this doesn't have basis for anything, all right, let's crank it up a notch and make it a little bit more exciting. So let's look at this. Find probability that if a family has 3 kids, two will be gross. And since we mentioned before that observed probabilities aren't exactly equal, we're going to assume that there's an equal chance boy and girl. That's an assumption we're going to make. All right, well, this problem gets a little more exciting. So how do we do it? Well, we're going to start looking at this from the procedure point. What's the procedure for this problem?
Girl, boy.
No, that's an event.
So just like all the options is how the kids would come out.
Sample size?
So like could be 2 boys, 1 girl.
No, procedure is having 3 kids.
Oh, 2 out of 3 or
It's kind of hard to talk about a family with 3 kids if you don't have kids. Right? It's kind of hard to talk about American company which has a headquarters in Ireland, right? Right? So this. All right, so the event is 2 girls, and I already heard one mentioning. Is there anything more to it? To this event, right? Event is what we are looking for. Procedure is what we're going to do to do the experiment, right? So event is what we want. We want 2 girls and 1 boy. There's a very specific option choices. Either you have a girl or a boy, and you need 3 of those. 1, 2, 3. All right. So now we're looking at probability of 2 girls plus and boy. And now we go to the sample space. Right? Now we are looking at this problem and saying, hey, this is a classical probability. If it's classical probability, means every option has the same chance of happening. What are the options? Well, you have 3 kids. Well, you could have boy, boy, girl, boy, girl, boy, girl, boy, boy, girl, 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 boy, girl, boy, girl, and boy, girl, girl. 1, 2, 3, 4, 5, 6, 7, 8. Now you can do this systematically the way I did, or you can try to draw a tree diagram. You'll get the same thing. We did a tree diagram before with heads and tails, and now it's girls and boys. Okay, so now what we're looking for? Well, now we're looking for 2 girls and a boy. 1, 1, 2, and 3. Now, a question that usually arises is, what's the difference between girl, girl, boy, and girl, boy, girl, and boy, girl, girl?
The sequence.
Yes! Yes. How many of you have a sibling? Right? How many of you get upset if somebody came around and mixed your names up? Or your birthdays? Right? Yeah? Well, I have two brothers, so there's three of us. If somebody starts messing our names up back and forth, and I don't mean pronouncing my name like Jan, but actually messing up our names, I will get very upset. I'm the oldest. This is my place. Like, I'm the first one in line. Don't move me to the, secondary position. You know how it is. You're either first, and then you have the second person isn't second. They're the first loser. That's how I approach my relationship with my brothers. I'm the first. So we have three choices. All right, 3 out of sample space of 8. So 3 out of 8, which is 37.5%. And so here we should make this statement that probabilities are always between 0 and 1. So 0 and 100%. So if somebody says, I'll give you 110% effort, I go, bullshit. You're obviously, hiding something from me. There is no 110%. So, all right? Which means that probability that equals to 0 becomes an impossible event. If you have probability of 0 means that it's not happening. Well, in that case, what is probability of 1? Well, that's certain. It's a certain event. So if we have a probability of 1, means we are talking about it's happening, no way around it. And here we run into a problem. Since we cannot always use classical probabilities because we cannot convert everything to a very simple model like dice or coins, we are stuck collecting most of our data as observed. And so we should talk about what happens if we keep on collecting data. So here comes the law of large numbers. The law of large numbers says the more a procedure is repeated, the closer the observed probability will get to classical. So if you looked at this coin, you got some coin, you're flipping it, this is what you're getting, this is what the best information you can have. But if you keep on flipping it over and over and over again, a couple million times down the road, those probabilities will get closer to what they classically should be. All right. So far, everybody's with me? Yeah. Too slow? I can, no? All right. Well, we didn't talk about events happening. Let's talk about what happens if we describe events from the other side. We'll talk about complements. So a complementary event complementary events. It's events. Those are events which are mutually exclusive. Mutually exclusive means there are two events which cannot happen at the same time. All right. So let's define a complement. So a complement of event A is denoted as A with a bar across. That means complement of A. So we read this as complement of A. So A with a bar across is complement of A. And is all the outcomes and it's all the outcomes when event A does not occur. Can somebody give me an example? Vague guess. So let's say look at an event. You have a kid and it's a boy. What's the complement of that? For example, right? If you're looking at giving birth, right, boy and girl, right? Or if you're looking at the grand scale, you either have a kid that is a boy, or you have a kid that is a girl, or you don't have a kid, right? That's a complement as well. If you have a coin, heads or tails, right? Either you get heads or you get tails. All right. So let's look at an example that is slightly more complicated. Let's say we have, so example. The event we're looking for is rolling A5 on a die. Right, this is regular. For people that play in D&D, this is a regular six-sided die. So that's the event. We're rolling a 5. What's the complement of that?
1, 2, 3, 4, 6.
How about shorter? Can you shorten?
1 through 6. 1,
Well, 5 is 1 through 6.
2, and 3.
Okay, how about not rolling a 5? Right? The complement is all the outcomes when A does not occur. Right? A is defined as rolling a 5. So the complement is everything but. And since we are rolling a die, there is no other choices than 1, 2, 3, 4, and 6. Right? That's all the choices, but there's 6 choices, and it's not 5. All right, well, let's break out the. So what's the probability of the event happening? What's the probability of rolling a 5? 1 out of 6. Easy. How about probability of the complement of 5? 5 out of 6. Oh, guys, too easy. I have to up it up. All right. So a note we can make here, we are starting to see from this example, is that the probability of an event plus the probability of the complement must so probability of A plus probability of complement of A equals to 1. Now this is important, this will show up later. It's nice. So if you have a sample space, right, you have some options that will happen, right, or might happen, or have a chance of happening. And I say, hey, those things are event A, this is what I'm looking for. The complement is everything else, right? And we can divide a lot of things into that binary system of either belonging to one or the other. Okay. Additional. Additional. So when we start talking about additional, we have to start talking about compounded events. And so additional rule. Compounded events, let's call it. And we're going to say this is an event What's a simple event? Yes, right. So simple event is a single outcome, and an event could be a single outcome, but the event could be something more than that. Right? 2 girls and a boy. Right? That's an event. So a simple event would be just a boy or just a girl. Right? And so we started looking at compound events where we have one event that joins a bunch of little things together. Okay, so example. If I remember correctly, this is the class that has all the gamblers in it. So if I start talking about crabs, everybody will understand. For people that either don't want to admit or don't understand, crabs is a game where the simplified rule saying you win if you roll a 7 or 11. It's a very simplified version of it. So let's say we are at the craps table, we roll the die, and one of them stops. So one of the dice stop. On a 6, right? Since our brains are supercomputers and you guys are getting so good at statistics, right? What happens? Well, your mind starts trying to figure out all the options to get to either 7 or 11, right, to win. So what are the options? Well, you could roll a 1 or you could roll a 5, right? This would give you a 7, this would give you an 11, right? So what's the probability of winning here? A third. How did you get that?
6 options, and you have 2
right? This is 1 out of 6. This is 1 out of 6. So in our case, the probability of 1 or 5 is 2 out of 6. Again, this is a very premature example to what we're going to talk about, but one that should give you an idea of how to do it, right? The probabilities. Probabilities for both cases. To roll 1 out of a 6-sided dice is 1 out of 6. To roll a 5 out of 6-sided dice is 1 out of 6. Okay.
I don't get what.
Sorry.
1 or 5, it's 2 or 6. It's 2 to 6.
1 or 5.
Oh.
This already landed. This landed. Right. Still rolling. Right. You roll the dice, one stopped, the other one is about to fall, and you have a split second of frustration of trying to figure out what are your odds of coming home with money or not. All right. Let's go here. So I have this notation here, probability of 1 or 5. So in this class, we're going to say the probability of A or B is defined as probability of A occurring or probability of B occurring or both A and B occurring in a single trial. Now I might write trail at some point. Just assume that if I write trail, I mean trial. I'm dyslexic. I tend to make that mistakes even if I know which one to write. So or in math means one or the other or both. Okay. So let's say the HR department comes in here and they start giving out prizes. And the prizes go to people that are, I don't know, say, females or wearing blue. Let's say we have this. Somebody comes in and starts doing it. Well, how many people what would be the probability for this? Now, we're going to get to how to calculate, but let's look at how many people we would grab if we do it. Well, female, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Blue, 1, blue. Blue. And don't show me your underwear because that gets me in trouble. So like blue, pants, shirt, t-shirt, right? 1, 2, 3, 4, 5, right? Jeans. 6, right? Suddenly we have this, 7, there's blue, there's jeans too, right? Yeah, but we're counting either female or wearing blue, right? So we have this. If we looked at this as probability, right, we're going to figure out how to calculate probability in a second. But let's say we're doing it, we don't do probabilities, we're just going to give out prizes. Right? Well, female, okay, you get a prize, 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 right? And then blue, you get a prize, I get a prize. Hang on, you already got a prize, but you get a prize again. Right? How many of you would be comfortable if suddenly people would get double prizes just because they fall for 2 categories? Not cool, right? Well, you would get 1 prize, but he wouldn't get none, right? So suddenly there's this level of question of like, hey, something wrong with it, because if I start counting just like did here, I counted one, I added the other one, and suddenly we were good. Here I add one, I add the other, and suddenly something is not, not working. Like we have the feel for if we line people up, suddenly their names are popping up twice on the list. So let's look at an example, a bigger example. This is a really cool example I really like. I stole from somebody else, so I don't remember from whom, but we have let's say we have a courtroom, and we divide people into the following sets. We have guilty, not guilty, and didn't do it, and did it. Whatever they did, they're guilty, fine enough. And we have some numbers. Sorry? How many of you heard the term false positive before? What's a false positive?
Negative.
False positive is negative. Love it.
So when an alert triggers, but it's just a false alarm.
Yeah. Right? For example, a positive pregnancy test where the person isn't pregnant. There's a false positive that will get you frightened, right? So a false... Okay. So... Right? You're found guilty and you didn't do it. That's a false positive. So what's a guilty and did it? Well, that's a true positive. Not guilty, didn't do it is a true negative. And did it, but wasn't found guilty is a false negative. So just in case you wonder when people talk about false positive and false negatives, this is what it is. All right. So we have this beautiful table. So how many people are guilty or did it?
That did it.
Guilty or did it? Well, so let's say guilty. 1172, right? That's all the people that were guilty. And then did it? Well, did it. 72 and 9. We run into a problem, right? So this is guilty, and this did it. Did it? Guilty. But if you look at this category end up being counted twice. Why? Well, because how we collected information. I said, well, let's pick up all the people that are guilty, those and those, and let's pick up all the people that were guilty. Oh, sorry, guilty, those and those, and people that did it, those and those, right? Same as this here. Females wearing blue would get 2 picks, right, versus 1. So suddenly one of those is problematic because it has been double counted. Right? If this is a courtroom or a big holding facilities or whatnot, right, with all the people, you have everybody belongs to one of those 4 squares. There is no extra people, right? So suddenly when you do this, you're pulling out people and guilty twice. So if you decide to build prisons for this, for people that did it and are guilty, you're going to have a lot of empty cells because you cannot have a person in both spaces, right? Example, well, here's an example. Let's say you're wanted for murder and you wanted for burglary in 2 different states. Possible? Possible. Where are you going to go to prison? Both or one of them? One of them. Hopefully not both, right? The governors will come around and be like, I take the head, the left leg, right arm, and the kidneys. And you can have the rest of it, right? So that's why this is this. Now the problem with this, why we take one of those, is because those 2 events are not mutually exclusive. Right? They are not mutually exclusive. So we are having a double count. And we need to remove the double count to do it. Because the next step after doing this counting, the next obvious thing we did in this class will be the probability of guilty or did it. And actually for probability of guilty or did it, right? How many people are in this, let's say, court? I counted 177, right? So the question is, out of 177, how many people are fitting one of those descriptors or both of those descriptions, right? Guilty, did it, and then both guilty and did it, fitting both. So there's what? 92? Right? (11 plus 72 plus 9, 92. Questions? And for people that are curious, this is about 52%.
What if there's like more than one trial? So let's just say they wanted guilty and not guilty. So we're adding, you know what I mean? So if there's 2 11s and 2.
So hang on. If this is saying, hey, I'm going to come in here and I'm going to try to pick at random somebody who's guilty or did it. I'm picking a person. What are the chances I'm going to hit somebody who's guilty and did it? Or did it, sorry. Not and did it, or did it. Right? Then I'm doing. If you're saying, hey, I'm going to pick somebody who's guilty first and I'm going to pick somebody who's not guilty later, that's a different story. If you want to pick somebody who's just guilty, that's 83 out of 177. Right? If I want to pick somebody who's not guilty, that's 94 out of 177. But here I'm picking one or the other. Okay, so let's put this whole rule in a slightly more mathematical description. How are we doing? So the addition rule. The addition rule says, hey, right, so far this is what we've been talking about, but it requires elimination of any double count. Right? We cannot count those people twice. So how do we do it? Well, it's P of A or B equals. Well, how did we do this? Well, we said we're going to take all the guilty. So that equals to P of A. Then we added what? We added the second event, which is P of B. Then we said, hey, we're going to remove one of the double counts. And which are the double counts? The double counts are ones that are both guilty and did it. So minus of A and B. Now, the important part, this is all done in a single trial. And that's important. We're going to deal with this AND thing later. And it's going to mean something slightly different. So
when do we use that?
this,
The equation?
when we deal with addition, or when we deal with statements, say, what's the probability of guilty and did it? So let's look at event A is guilty, event B is did it. Event A, those two, right? Event B, those two, and then A and B together, which is this. So you have 11 plus 72 plus 72 plus 9 minus 72. So this is how you do it. Okay. Questions so far? Anybody? Okay. All right. Let's take this out. There's also a term called disjoint events. So disjoint events are events which are mutually. So events that are mutually exclusive. And mutually exclusive means silence. Exactly. They can't happen at the same time. So mutually exclusive means they cannot happen at the same time. So the way I found best to illustrate it is using something called the Venn diagram. So if we look at two cases, if we consider this to be probability of A, this being probability of B, then this right here will be considered probability of A and B.
A and B or union? Oh, union.
Union is A and B. Right. Same thing here. If we have then the probability of there is no probability of A and B. Right. We can consider this, for example, can consider, for example, guilty and did it, right? So there is people that are both guilty and did it. And we can consider this to be rolling A1 and or rolling A5 and not rolling A5. Questions? Right. So if we take a look at this, so in this joint sense, there is no overlap. Thus, the probability of A and B is 0. Right? So for example, rolling a 5 and not rolling a 5. What would be a good example? Long distance relationships. Probability of meeting you or your spouse. If it's a long distance relationship, they're in Kansas and you're here. The chances of you meeting both of you at the same time is impossible, right? You're mutually exclusive. If you live together, there is a chance of just meeting you, just meeting your spouse, or bumping into two of you at the same time. Okay, so we're good on that. All right, so let's do some examples. So, examples. Let's look at example number 1, the probability of selecting a diamond or a club. Example number 1. Let's look at example number 2, the probability of... I'm talking about a standard deck of cards versus a blackjack shoe. Standard deck of cards. Selecting a queen or a spade.
So you said that the first one was what? The first box?
It's a diamond.
Diamond. What's the one next to it?
A club. Okay. I feel artistically accomplished today. Yeah, I want to see your notes. Single color. Like orange, there was blue, now it's red. Painting inside of the lines, I'm very good at. All right, so the first one, probability of selecting a diamond, a single deck of cards. How many diamonds are there? Right, there's 13 out of 52 cards. How many clubs? 13 out of 52. So the probability of diamond or a club is, well, this is 1/4, right? It's 1/4 plus 1/4. Is there any overlap? Is there a card in the deck where you can pull a card and it's a diamond and a club at the same time? Right, this is single trial. So there's -0, right? And for people that said yes, stop playing Magic, dual color decks are bad. All right, let's look at the second one. Probability of a queen and a spade. For this one, I'm going to write it out. So probability of a queen or a spade equals the probability of pulling a queen plus probability of pulling a spade minus probability of queen and spade. All right. Chances of picking a queen. So 4 out of 52. Chance of pulling a spade. 13 out of 52. Is there a card where if you pull it, it's a spade and a queen? Yes, it's a queen of spades. And there's only one of them. That's so the whole thing comes out to be what? 17 minus 1, 16, 16 out of 52. Which comes out to be what? About 30.8% or so. Everybody so far with me? Good. All right, so if we go back to complementary events, we knew that probability of right, you either were one or the other, and you couldn't be both at the same time. Well, so that would be probability of A plus probability of right? I'm just writing this out. We know it's 1. I told you it's 1. And I'm writing it out. If I write it out, this should strike you as interesting. The complements are mutually exclusive. If they are mutually exclusive, then this is 0. Right? It's an empty set. Because they are mutually exclusive, they don't overlap. So we come down back to that. But if we have this is a mathematical equation, which means that right, I can subtract probability of complement of A from both sides and get this, or I can subtract probability of A from both sides and get this. Which tells you what? Tells you that if you have mutually exclusive events and you know the probability of one, you know the probability of the complement. Or if you know the probability of the complement, you know the probability of the event. Right? This tells me, because we know what one is, we can deal with one. It's a number, it's very good. So if you know this, you can get this. If you know this, you can get this. And this is surprisingly powerful when we start dealing with it. All right. Let's go further. We know that we have We know. We have an observed probability for the birth, or for the natural preference for girls being born versus boys. And it's observed. It's an observed probability. We know this. We've been measuring things around hospitals, and girls are born more often than boys. So what's probability of a boy? Well, probability of boy and probability of a girl are complements of each other. They're mutually exclusive. So probability of boy equals probability of the complement of the girl, right? Probability of boy is the complement of probability of the girl. Now I understand this is a very simple example, and we jump to the boy to girl to 1 minus that works, but let's think about it in terms of, if I ask you a probability of the boy, we know the probability of a boy is the complement of probability of a girl, which means that complement of probability of a girl is 1 minus the probability of a girl. So that equals to 1 minus probability of a girl. Right? So the probability of a boy equals to 1 minus 0.512, which equals to 0.48. Okay. We have 6 minutes left. Should I keep going? Start.
Where did 8 come from?
1 minus 0.512.
Yeah, you make your points in the comma.
European thing.
Yeah.
It's easier for me than to make it dots, because sometimes the dots are not visible if I just stab it. But I will do my best to be clear. That's why I try to write my ones with a little dash, so you cannot confuse a point and a 1. But I will try to be more consistent. Okay, we have 6 minutes left. Should we start going in the No.
I'm mind blown.
Mind blown. Mind blown.